Okay. Okay. Good morning, everyone, and welcome to the IMechE webinar on asset integrity, improved safety, increased production, and reduced costs. I'm delighted to be chairing today's webinar. We've got a fantastic set of speakers involved in the webinar. The webinar emanates from an initiative we're trying to lead as the IMechE of how we can support the process industry operators to both enhance safety, increase production and reduce costs simultaneously through how they implement asset integrity, and that's through the adoption of new technologies, advanced AI, and non-invasive techniques. So you'll hear a lot about these as we go through these, as well as a lot of the process safety challenges we have in the high hazard process industries in there. Just some housekeeping before we start. So the event is recorded and it will be made available on the Process Industries Division YouTube channel. Everyone will be muted apart from the speakers in there. We have a number of speakers you'll see in a minute. If you want a CPD certificate, please let us know after the event. And any questions, please put those through the questions and answers in there. And speakers will be allowed to share their slides post-event as we see fit, but there will be a recording which will have the slides on it as well. And as per IMechE policy, AI chatbots are not permitted to create notes on the transcripts in there. You see on the top right-hand side as well, we will have a 4-poll questions as we go through this. So, and you'll see this Slido on a couple of slides now. So if you can scan that on your phone, you'll be able to participate in the poll in there. As the IMechE, we believe in equity, diversity, and inclusion. So, bringing people from different cultures in there and making this open to the wider engineering community in there. So a lot of work's gone into producing this webinar. So we've had a number of months of discussions on this webinar and what we're trying to create post the webinar in there. So hopefully you'll find that beneficial as we go through. This webinar can only be created by the help of our speakers. So I'm delighted we've got 6 speakers, including myself, 5 other speakers, Richard Hellebrand, David Glass, Harry Moss, Jonathan Lowe, and John Wiggins, majority of whom are from different parts of the IMechE, as well as day jobs in there. And they will all be giving their inputs to ensure we have a balanced input of how we can improve safety, reduce cost, and increase production through the implementation of asset integrity. I'll let each speaker introduce themselves as and when their input starts through the webinar. So this is the agenda. So I've got 20 minutes to take you through the introduction. Then I'll hand across to Richard. Then we'll go across to David, Harry, Johnny, and then John Wiggins. And then I'll come back and we'll take questions and answers with Richard to help in there, and I'll take you through sort of what the call for action is and how maybe you can help support this as well. And please don't forget the Slido at the top in there. I only have 2 slides on TUV. So we've been in TUV for 2 years now. So we were part of ABB in TUV. TUV, German company, and it's been operating since 1872, and it supports people maintaining safety across their plants. Has 5 different business streams, 24 different business fields. And within the TV Rhineland in the UK, which I'm part of, we have a number of sort of capabilities that resonate around the subject topic today. So they'll be in the slides. Why are we here today? If you look at the news, we have very challenging markets at the moment, especially across Europe, high energy prices, aging assets, skills shortage, cost of living, inflation, impacted even further with the Ukraine war. And that's resulted in a lot of operators in chemicals and refining with reduced margins and much greater increased global competition. And in the last 12 to 18 months, we're starting to see tariffs as well in there. So that's some of the climate in there. But for me, 2025 has been quite noticeable on some of the announcements we've seen. So the first one is Petro-Ineos in Grangemouth, around the refinery being shut down. That was announced last year, but in April it started its shutdown. Unfortunately, SABIC have an ethylene cracker on Teesside that's been shut down for a while for a large revamp and decarbonisation project, and the decision was not to start back up that, with the resulting number of job losses in there. In July this year, you'll have seen Prax as well gone into administration, and that's a refinery in Humberside. Again, takes capacity out, takes a high hazard plant out as well. And lastly, Vivergo, again, in the Humber region, and the bioethanol plant has decided it can't operate competitively. So quite a strong sort of market around the competitiveness in European chemicals and refining. And if you look at the top left-hand side, European chemical sector on the brink of extinction, that I didn't make that up. That's on the INEOS website. INEOS is, you know, the second largest chemical company in Europe, and that's on their website. So we're seeing strong headwinds in there. And the question is, what can we do to help in there? So my background, I spent 4 years within ICI as a turnaround manager. So I just wanted to talk about how asset integrity and major turnarounds have an impact. You will see in the top right-hand corner is the turnaround manual we had in ICI, so that issued in 1995. In there, turnarounds are tend to be infrequent events. Maybe we do them every 4 years, 5 years, 6 years, depending on the plant in there. Some plants do them a lot more often, but we see lots of confined space work, bringing a lot of contractors onto site. In there, the complex events, we have invasive entries, multi-level entries, critical path and bulk work tend to be big elements in there. What we do find, though, is the biggest element of turnarounds for refineries and chemicals and petrochemicals tends to be asset integrity scope. So that tends to be the biggest element of scope, unless there's a project happening at the same time in there. And we have this large event that we spend millions on. We bring a lot of strangers onto site to actually do some work. But what that event also does, it defines the asset integrity and reliability of the plant for the next 2, 3, 4, 5 years, whatever the interval is between the turnarounds in there. So how does asset integrity impact turnarounds and business profitability? Turnarounds tend to be the single biggest contributor to business performance in the financial year they're in. And that's from the maintenance spend, that's from the lost production, availability, OEE, production efficiency, whatever you may call it, and potentially also safety performance, because you've got lots of work you're doing, and you saw the complexities of doing that work. I think the right-hand side, it's a bit old now, but it's Oil and Gas UK data on the failure or uptime data in the UK offshore sector. So that's for every offshore operator in the UK, and it looks at what is the plant downtime. And you can see annual shutdowns was 20% of all downtime. So if you went to an average facility, 20% of the time in any annual year, they weren't producing. And then 48% was from plant equipment failures and unplanned shutdowns. Obviously, not all from asset integrity, because you could have rotating equipment and so on. But again, a big chunk will be in there. So asset integrity has a huge impact around the business profitability in there, both as an output around the performance of the plant, the safety of the plant, but also as an input on what we spend on that plant. And when I was in the turnaround team, we always used to have a saying: to succeed in a turnaround, you've got to get everything right. To fail, you can only have to get one thing wrong. Again, that comes back with the complexities of turnarounds in there. Okay, so I'm going to go to the first poll question. Do you believe, as engineers and managers, given what I showed before, we're doing sufficient to optimize the impact of asset integrity on the production output on operating plants? And you saw what we talked about the UKCS. I don't believe that exists in our onshore for what the impact of asset integrity has on there. Maybe others will have more data than I have. So the answers you've got: yes, our turnaround intervals and durations are optimized. Yes, we have greater than 90% uptime and OEE, or whatever is good in your industry. No, I believe there's room for a step change, or no, I believe there's room for marginal improvements. It'd be good to see what people think as a response. So it looks like we've had 26 people vote so far, 27, 30. I'll just let people vote. We're going to do 4 polls. So once you're in on your phone, it'll be a lot easier to vote for the next ones. Once we get to 50, let me just give it another 30 seconds to get any people to finish voting. So the question is, do you believe as engineers and managers we are doing sufficient to optimize the impact of asset integrity on production output on the operating plants? I guess I'm talking predominantly to engineers here. So we may have a different answer to maybe the economists or the plant managers or the site managers. Okay. So there's our response. And I think this is part of the justification why we want to do something as the IMechE to make it to change things. Okay, let me move on. You'll still be able to vote, but I'll move on. Okay. So what we're trying to do is the IMechE. We want to try and transform asset integrity. It wants to be balanced. We don't want to have a safety incident. If we have a safety incident, it has a huge impact, whether it's on a turnaround or whether it's during operating plants. But we want to enhance the safety performance, increase production, and reduce our operational costs. That's what we want to try and do. And we want to try and bring industry together to look at how can we do that, utilizing the new technologies around. We've got AI, but also upskilling people on operating plants and people that support operating plants across there. Okay. On the right hand side, you'll see Formula One. It was the first Formula One that was run 75 years ago. And in 1950, the average pit stop during Formula One was 67 seconds. In 2025, so 75 years later, we're talking about average pit stop between 2.5 and 2.6, 2.7 seconds, and the fastest is 1.94 seconds. So we've seen a radical step change around how those cars perform and how we maintain those cars in there. So what we want to try and do is bring that same force, bring that same thinking into the high hazard process industries. It doesn't mean we will do our turnarounds in 60 seconds or 2 seconds, but it does mean is we will adopt the technologies that we see in other sectors into the high hazard sector in there. So more effective asset integrity strategies, shorter and more cost efficient turnarounds, maybe increase the interval between turnarounds if we can as well, but improving the uptime and production output. So that's what we're trying to do. This webinar is a call for action for this. Why are we doing it? I think for me, the right-hand side shows you what the cost is of actually going inside equipment or having invasive entries inside a lot of equipment. The cost of inspection is very, very small, which is the green. The yellow to orange is the cost of actually getting inside equipment, the scaffolding, the insulation, etc. And then the red is the lost production. So you can see a huge cost in there. If we understood what the condition of equipment is, maybe we can do things differently and we can transition to what we see on the right-hand side. I'm not going to go through this slide, one for time, but also David Glass will talk about this in his slide as well. But in the UK, there is no legal requirement to go into pressure vessels. I know that's different in different parts of Europe, though. But I'll let David go into this slide. I've just put 3 slides in, which is the case for change in there. And then I'll hand across to the other speakers. Sorry, upstream. So back in 2017, we were then part of, I'm not sure why this moves on. We're then part of ABB. We actually conducted a study for the Oil and Gas Technology Centre to look at how we can support upstream operators and what's stopping the uptake of advanced technologies and non-intrusive inspection in there. So we conducted a survey across a number of operators. Apologies, the slide's going on its own. number of operators. And what we found as the outcome is there was a low level of NII usage in the basin. There's a potential when we did interrogation on a number of companies for a 42% cost saving in there. I know some of these facts are disputed, so in there, but for me, the biggest thing is there's a lack of visibility across many operators of what the true cost of asset integrity. And this is another picture of the same things in there. And there's many barriers for uptake of technology, behavioral and commercial. It's not just about the technology. And the slides moved me on, so I'll talk about number two. So number two opportunity for change was a study that we did from 2020 to 2024. And that was to implement asset integrity across a number of refineries and ethylene crackers in Europe. So there was an opportunity to reduce it. The main reason this study was conducted was to stop the unplanned outages and stop the failures. It wasn't to cut cost, it was to stop the unplanned outages and failures. But what we did find is by emboldening asset integrity, by digitalizing asset integrity across the sites, looking at equipment criticality, corrosion control, and so on, we were able to bring new inspection techniques and new ways of working that actually supported OPEX cost reduction, improved safety, and improved uptime. And I'll talk about this a bit at the end as well around some of the values we did there. What we also did for the operator right at the start is produce this thing called the value gap. And you will have seen that value gap when we talked about offshore. And this is one of the deliverables we'd like to see for the joint industry project is what is the value gap for us to do something differently? And what are the challenges for us to do something differently? The last opportunity for change, really, and I've got to thank some of my colleagues for producing this slide who are more technical than I am, is some of the techniques that are available now that people can utilize to reduce shutdown times through different NDT techniques. And whether that's eliminated radiography by using techniques where we don't have to take people off the plant, which is number one, replace internal inspection, talk quite a bit about that, and so on. And then also some online techniques, time of flight, phased array, ultrasonic, pulse eddy current, and so on. So the whole set of techniques in there. And how do we make those more accessible, more affordable, but also people understand when they can use them and what their limitations are, those techniques in there. We've also seen a lot of drone usage and robotics and how that can benefit as well. So how can we bring that into how we conduct asset integrity, and then data analytics and artificial intelligence in there. The last part we won't cover in the JIP, but there is a webinar in a week and a half's time by the IMechE that will cover this, and you'll see that on the end slide. This is a true example of a vessel that was suffering, commissioned in 2001, pit like corrosion, internal pit corrosion in the vessel, widely across the bottom. It's a spherical vessel in there. And so we knew its degradation mechanisms are, we'd done an inspection in there, and we knew what was causing that degradation. So what we then do is then look at how can we actually take this, knowing this degradation mechanism already in place and we need to monitor that, so how can we actually monitor for that without necessarily going inside? And on this one, we're actually monitoring it online, on stream, in through corrosion mapping and utilizing phased array, hydroform phased array in there. So inspection plans were drawn up to change the inspection regimes in there. And then we also looked at other challenges we had to do. Did it eliminate the intrusive? It didn't, but it enabled us to actually capture more data on it, have more understanding of the degradation, so we could extend the interval on this facility, even knowing the degradation. And we don't just introduce it. You see on the right-hand side, you go through a scoping, a technical analysis, an approval process before you execute it, and then you evaluate the results. Because what you're trying to make sure is what we're doing non-invasively has the equivalent or better result than actually sending someone inside a vessel. That's all I'll say on that. I know David Glass will touch on this a lot more around some of the limitations. Okay, poll question number 2. What factors have driven the technology advancements we saw in Formula One that have enhanced both safety, Formula One cars are safer than they've ever been before, and performance over the past 70 years. What's driven that? Maybe that's lacking in our process industries. And this is a cloud form. If you can type your responses in there, short or long, it'd be just good to just understand what's driven that industry that we're not seeing in our industry. So competition, as a service provider in the high hazard industries, I would say there's a lot of competition in the high hazard industry. Investment, maybe innovation, budget, regulation, FIA safety. We in willingness to adapt, mindset. I saw right at the start, motivation, wanted to win. Okay, all right. I'll move on, but people can still vote. But I'll move on to the next slide. Okay. So 3 minutes late, I'm afraid. So I'll hand over now to Richard. So Richard will be the first of our speakers, and he'll talk about the required process safety focus we need in our asset integrity techniques. Richard?
Yep, hopefully you can all see the slides. So very briefly, I was a responsible engineer in charge of chemical plants for more than 30 years. So done the asset integrity bit, but also a lot of process safety, and my current job is advising on process safety around Europe and Asia for a multinational company. So I get to see a lot of horror stories. I also get involved with American owners as well. So plenty of stuff. And my email address, I always put this on the slides. If you want to get in touch with me afterwards, I'm quite happy always to chat about process safety aspects. So, isn't it a given that we have process safety? Well, we do need to work smart. We know that on their asset, maintaining assets through the life, because we've got to get the costs down, and those come from breakdowns, shutdowns, turnarounds. Alan's already alluded to that. And some of the speakers will talk about some good modern practice that can do that, but I'm really concerned that process safety implications could be overlooked. So I'm going to look at a few examples of failures that were avoidable. And they include small near misses, well, big near misses, if you like, and small events, but they were almost disasters. Unfortunately, I have a whole catalogue of these things I could share, but I'm not really allowed to because of confidentiality. So the fact we're repeating these things, it sort of hints at declining technical competence and knowledge in the industry. We want to arrest that, obviously. Just this pie chart is compiled by 36 European-based multinationals, chemical companies. And to give you a feel for this, the combined working hours for those incidents was 2.5 billion working hours. This is a lot of companies, and that all of their internal incidents that have either CEFIC based or API tier 1 and 2 based are reported and analysed. And you can see more than half are operations, and when we look through them, really we're talking about human factors, and then a third are asset integrity as well. Now, which is actually there's no clear dividing line between them, because knowledge can often lead to asset failures. So I'll give you a few examples. I'll start off with flanges. Now, this is from 2021 in the US. They were trying to start up a hydrogen fluoride unit. An operator noticed a small leak at a flange. He went over with his BA on and checked it, radioed for help, and another operator came over, but the joint suddenly blew out. And the second operator didn't have the right PPE. He died. But 14 years before, they'd identified corroding spiral wound gaskets as a problem in these duties. They found a better gasket, but they decided just to wait for them to fail or to change opportunistically rather than proactively. And that resulted in someone dying, because you can see from the photo on the right, we had stretch bolts, and then obviously it failed, and you can see the state of the gasket. Another example, this was from last year, and this was a large monomer in the Netherlands. I've got a photo of the actual sphere, but I haven't got permission to share that, so I'm sharing a freebie off the internet, but it's a very, very similar looking sphere. And they were loading vinyl chloride monomer from that sphere into a ship in the nearby harbour when the gasket, which is a tanged graphite gasket, suddenly failed. And you can see the photo on the right, that is the actual leak. And it's a nightmare for maintenance people, or anybody really, because it's the first gasket after the sphere, it's non-isolatable. Now, they flashed off nearly 2 tons of vinyl chloride during the incident, but most of the sphere they were able to empty it into the ship. Now, if you haven't come across vinyl chloride, it's very similar to LPG, very, very flammable, but it's also a carcinogen. So it's not a good day at the office when this happens. Luckily, it didn't ignite. No jet fires, no explosions, nobody hurt. But this is in central Rotterdam. It could have, if that went up, it would have taken out a lot of Rotterdam and killed people. When I got the details from the company that did it, it turns out they hadn't got a procedure for tightening bolts up on high hazard flanges. And so the bolts were under tensioned. Now, these are a couple of slides from Chris Mellows. You may have seen these before. There's the link there on the bottom of some of the defects he comes across in his company, Zulu Joint Integrity, when they inspect, mainly in turnarounds, the quality of the joints being put in. You can see some absolute horror stories in there. The worst ones being the use of grinding discs gaskets, but short bolting or modifying the gasket or over tensioning are also common. And this, again, this goes back about 15 years when he first started his business. About 8% of what he inspected was defective. It's now up 14%. It's going up. So for the last 10 years, that's a straight line going up of badly installed gaskets. Now, a process safety event requires a loss of primary containment. Well, the easiest way is for the gasket to leak. And so this is going to get us in real trouble if we don't sort it out. Just a little bit about corrosion. I'm not going to go through all this. Corrosion's complicated. But if you're in asset management and you're in an industry where corrosion takes place, you need to get some expertise on this. And if you don't have it, you need to have someone on call who does. But I'm going to pick up a couple of things around stress corrosion at the bottom. Really just chloride-induced stress corrosion. There's plenty of mechanisms I could talk about, but time's short. To give a couple of examples. Firstly, what is it? Well, it happens in insulated austenitic stainless steel pipes and vessels. It's dictated really, the cracking, by the temperature and where the chlorides are present. The stresses are always present because most of this equipment is welded, so you've always got stress in welded equipment. And the chlorides can come from pretty well any source. That could be in the insulation, the process itself. They could be just on the wind, or even tap water if it's the wrong tap water. So even low concentrations are enough to start the cracking. And anything above ambient will mean that solution with the chloride evaporates. Well, as soon as it evaporates, the chlorides concentrate up, and eventually they start filling up the little cracks and pits that start that are obviously available around welds, and they become stress concentrators and start it off. You might not even notice it's leaking because they start off as tiny little cracks. Now, I've just got a photo on the right, a couple of photos. This is the big one on the bottom right. It's what the surface looks like of a pipe, but in cross section you can see in the cutaway the cracks are progressing their way through the pipe wall thickness. Now, they won't leak until they get through, but when they do, you might start off with a really small leak, but it could turn into a really big leak. And it looks similar to sort of general fatigue. So the difference is it doesn't need cyclical stress, whereas fatigue, you're putting, compressing and expanding and moving stuff around. So the example, I won't say where it is, but it was in the UK in 2017. This was an ethylene gas compressor. It tripped. It got a 6-inch recycle line around the compressor, and that pipe split. And it's a stainless steel pipe again. You can see the photo that I think an HSE inspector's holding their pen against it, but it was a 10-inch long crack. This is the pipe without the insulation on. 17 tons of ethylene gas leaked out, forming a very large gas cloud. Luckily, again, it didn't ignite, but it was near to cracking furnaces. It could so easily have happened and become a disaster. And I think a year or so ago, the company was fined about 400,000 for that. Root causes, chlorides and stress corrosion, and it's next to the coast. They couldn't find anything else that could contribute the chlorides. There'd been an RBI study, so that's risk-based inspection, to set an inspection strategy. Nothing wrong with that. It's good best practice. But they'd made a mistake, the team. They'd adopted a corrosion loop approach. And they bundle the recycle pipe comes from the discharge to the suction. Really, it should have been attached to the discharge for the study. They grouped it with the suction. The difference is that it suction's minus 100 centigrade, whereas the discharge above 80. And because of that, they assumed that stress corrosion wouldn't be possible, and they didn't strip off the insulation to check. You know what they say about assume. And then another one. This is my own plant near Blackpool at the time. And this was the average minimum temperature on the graph on the left from 1990. And I think all of you who lived through 2010 recognise that it was a terrible winter. Way, way colder in November, December than we'd ever had before. And you can see the icicles hanging off pipes, this photo that I've got from the plant. After the thaw, my electrical engineer, renewed all of the electric trace heating with better stuff, because he thought that'll stop it. It'll never happen again. He didn't check with me, and he didn't do an MOC, a management change. So over the next 2 years, quite a number of these newly traced stainless steel pipes failed, and there were lots of leaks. And the root causes, well, again, that plant was that Blackpool's near the coast, so you get the salt and the chlorides welded, obviously. In fact, it was these pipelines were continuously welded. Now, the pipes hadn't corroded for 30 years at all before then, but when the heat tracing was put on, the spot temperature reached 90 degrees, even with thermostats. I did some trials, I could prove it. So you get a sawtooth effect. Although it might maintain a nice average low temperature, the hot spots were very, very hot, and that started rapid stress corrosion. Another example, this is safety valves. You'd think that safety valves are 101 for protection against pressure events. And I did some audits in 2022 and found a whole bunch of safety valves wrongly installed. When I say a whole bunch, around 200 safety valves across some plants. And the installers had not conformed to the original equipment manufacturer's installation instructions or to the technical code that refers to, which is API 520. And basically what it is, on a balanced bellow valves, you have a little bellows, I don't know if you can see it, and the cutaway, and it's to sort of insulate the setting of the valve, isolate the setting of the valve from back pressure. And this happens in long discharge lines, for example, to manifolds. But for it to work, the bonnet on the top has to be vented to atmosphere. If you don't do that, if the bellows leaks internally, you get a build-up of pressure in the bonnet itself, and it can equalize, and effectively you end up with a blank flange, not a safety valve. So very serious. And the manufacturer shipped these with transport plugs and warning stickers to remove them. But they'd all been left in, including the warning sticker, and often painted over. And some of them valves were even tagged as OK by the inspection authority. No paperwork to justify that. And the engineers didn't know they had a problem. And I'm not talking about young graduates here. I'm talking about people in the 50s as well, who just didn't have that knowledge. A couple of photos. You can see clearly the plugs left in here, the warning stickers. This is in German and English. And sorry, Alan, but a nice TUV tagged, lead sealed cap on it to say everything is great. It's not. And this one's painted over. That's the sort of end of the examples, but I meant turnarounds are dangerous, potentially very dangerous. Hopefully we'd never get anything like Texas City. Lots and lots of people were killed and injured. And it happened during startup. I'm not going through the details, but you'll find it online. CSB have some great animations and reports. But this is temporary contractors. A lot of them were killed in the cabins. What do you do with your own cabins? Have you learned from this? Not just the other things. Have you actually learned where to put your people during the turnarounds? And even another turnaround, you can find plenty of examples of this. Cleaning catalyst out of a vessel. Basically, there'd been all this nice warning tape and signs on the top, had to be removed for the job to start. Someone dropped some duct tape in, mentioned that someone had seen some duct tape, and someone climbed inside to go and fetch it, and then his mate climbed after him. So 2 people died from nitrogen, confined space entry. So summary of this, there's lots of corrosion, maintenance, inspections, turnarounds, failures. They're not new, but to deal with them, you've got to have trained, experienced engineers and technicians. Many of the problems are related to aging assets, which we've all got. But if you're in asset integrity and maintenance, you know that you can extend, and we have to extend that bathtub curve to the right to extend the asset life. And it's very possible. It's not easy, but it's possible. But the biggest downtime is the shutdown. Alan's already mentioned that. They're expensive, they're resource intensive, horrible things to plan, and often result in startup issues, which add extra costs and can have the safety implications, particularly when we add in lots of potentially untrained labour. But yeah, we can reduce the need for shutdowns, or at least to their extent, but we've got to have competent people, and we have to assess the accurate condition of our assets. We don't want Mickey Mouse inspectors. We want really competent, experienced people. And when we've got accurate condition, then we can tailor inspection strategy. Then we can look at these other smart techniques and what can be used. If we don't share this knowledge, then people are doomed to repeat it. We're going to have safety incidents, hopefully not disasters, but it's possible. And certainly the failures and costs will carry on. That's me done. Contact me outside if you want to talk about any of this stuff, but you get the slides later. And Alan, back to you.
All right, thanks very much, Richard. All right, if I can, we'll take questions at the end, if you don't mind, Sean. What we'll try and do, we've got a number of speakers in there, try and stay on time. And then at the end, we've got half an hour allocated for question and answers. So across to yourself, David. So David Glass from the UK Health and Safety Executive.
Good morning, everyone. Hopefully everyone can see the slides. Just a little bit about me. I did used to sit on the other side of the desk. Worked in the batch chemical industry in the UK and in the US for 15 years, but then crossed over the fence to the regulator side quite some time ago. I'll discuss briefly the Health and Safety Executive, a little bit about the relevant legislation for asset integrity, and certainly in the major hazard sector, which is where I work. A little bit of discussion about ALARP, and I know there are other speakers. Steve might touch on that, and relevant good practice. But an example about non-invasive inspection, and I'll throw some hesitation in there as a counter to Alan's position. Some research findings from a project that we undertook about remote visual inspection as well, again, which offers tempers some thoughts. Touch on some thoughts of others relating to major accidents. And it's timely in many respects that the BBC are showing a series on Piper Alpha. So I'll touch on that as well, and then perhaps summarise our position. So, health and safety executive. So a little bit about ourselves. We regulate the workplace. I appreciate we have an international audience today, but UK GB residents will be familiar with this. We work in various different divisions. So typically, our inspection division and investigation division and specialist division support largely occupational risks and typically inspect on everything but major hazard sites. We also have the building safety regulator, which is post Grenfell, arguably a major accident there. And interestingly, the building safety regulator is adopting some of the practices that we use in the major hazard sector. My colleagues in energy division regulate the offshore sector. It largely come about because of Piper Alpha, which again I'll touch on. Work fairly closely with colleagues in energy division because, as you might imagine, we share a lot of duty holders in the onshore major hazard sector, similar fluids, similar risks, etc. My colleagues in science division, I work again closely with our laboratories who undertake a lot of research for us, but also investigation assistance, and publish some papers as well, which again I'll come to. My role falls within, and it's a bit of a mouthful, and forgive me for that, it's the Chemicals, Explosives and Microbiological Hazards Division. Basically, it encapsulates onshore major hazard risk in Great Britain. What we like to do is give advice in the first instance. We don't want to go further than that if we can help it. And thankfully, in most cases, we're dealing with relatively well-informed companies, and advice is where we stop. Part of our regulation, though, regards assessment, and some of you who operate coma sites will know that we assess safety reports for the riskiest sites. Our duties also extend to inspection, so we will knock on the door and come and ask questions of those people who operate major hazard plant. Invariably, when things go wrong, we undertake investigations as well. What we don't want to get to is enforcement, but occasionally we have to do that. So we try and stick to the basic end of advice. My role is slightly different to some of the others, colleagues that you may come across. I run a team who also undertake some research. So we take issues that we find from high hazard and asset integrity inquiries and incidents around the world and think, what is it that we need to do as a regulator to predict where the challenges and where the risks may evolve. So I initiate some of those with colleagues in science division. Inevitably, as you may imagine, as a mechanical engineer, our main focus is on aging high hazard assets, but recently some challenges with new and evolving technologies and new applications such as hydrogen and net zero, etc. Where do we stand with legislation for integrity? It's effectively goal-setting legislation. We're gradually moving away from prescriptive legislation in the UK, significantly moved away from that. Offshore, it's the PFIA regulations, as they're abbreviated to, and onshore, it's the COMA regulations, as they're abbreviated to. I've put the text there of the relevant part of the regulation. It effectively says a duty holder, or those who take the risk, must take appropriate measures, or all measures necessary to prevent a major accident. The offshore regulations are skewed towards fire and explosion, as you may imagine, the onshore regulations are a little bit more encapsulating and capture accidents to the environment too, which reflects the driver for that legislation, which was principally severe so. But nonetheless, what we're trying to avoid is disaster, both onshore and offshore. We do that typically using, I guess, the most accessible tool for us is the Health and Safety at Work Act, but targeting asset integrity are the provision and use of work equipment regulations. And it's incumbent on operators and employers in that case to maintain their equipment in an efficient state, efficient working order, and in good repair. So there's that's quite a high bar. You basically can't run it into the ground, is effectively what the regulation says. And plainly, to get to that efficient state, you have to keep an eye on it. So the inspection regulation dovetails quite nicely with the maintenance regulation. So if it deteriorates and if it's going to result in a dangerous situation, you have to inspect to maintain it in good repair. I should also point out on the onshore arena, we have the pressure system safety regulations, which is important because it introduces the concept of written scheme of examination. It talks about a competent person. It has other aspects to it. For example, you're allowed only to postpone an inspection once. So if it's qualifying equipment, anything over half a bar with a relevant fluid in it, you have to adhere to those regulations too. And there are some significant principles in PSSR that we extend in the COMA and onshore arena, like the written scheme, like postponement, etc. A little bit about as low as reasonably practicable. It's used in goal-setting regimes. It's not necessarily quoted in the legislation, but certainly the guidance to that legislation. It stems from the phrase, so far as reasonably practicable, which is used and quoted in the Health and Safety at Work Act. It's the reasonably practicable bit in there, which I think is we all have to remember. So it's founded on the principle weighing the risk against the sacrifice to reduce it. And there's a quote which accompanies the Health and Safety at Work Act. It's not a question of balance. An effort has to be made until it's grossly disproportionate. I think the key here is to remember the phrase reasonably practicable. What is reasonably practicable for us to undertake? If you remember that, I think most things will be okay. About making an effort, in the COMA guidance, I think we plainly have to admit and recognize that we are taking a risk when we actually produce chemicals, for example. We can't eliminate that risk. That would be offshoring it to somewhere else, and plainly we want industry in the UK. So we recognize that the risk exists. But what we do say is that we should consider that risk and challenge ourselves based on a hierarchy. So eliminate first, but then prevent, control, and then mitigate. So those are quite clear principles. In order to prove as low as reasonably practicable, in the first instance, we rely on relevant good practice. A relevant good practice is not hugely well defined. It's not listed anywhere, but it's generally a consensus. And the important part here is it's driven by industry. We have an input to it, but it's a consensus opinion amongst those who are best informed as to what measures are necessary. We lean on relevant good practice a lot. I guess this is the opportunity then to introduce what we regard as relevant good practice when it comes to non-invasive inspection. This has evolved over many years now. It's now hosted by Hoyce. There's a link on the bottom of the page, and forgive me, I couldn't put QR codes on. But if you follow that link, ultimately you can get to the Hoyce guidance. It is free. You may have to register nonetheless, but it is free. It's evolved over a number of years. We have had input to it in its various different forms. It is a very detailed and challenging process for the high hazard industries to adopt a purely non-invasive protocol. It considers the equipment history, so how has it been used, how many times has it gone beyond an integrity operating window or a safe operating limit. It talks about the inspection history and how reliable that data may be. It talks about the NDT coverage and its suitability. And it applies to individual inspections. It's not there to change a written scheme in its entirety. It's there to consider any one inspection, and can you change any one inspection to non-invasive? The inference being that the longer you go and the more non-invasive you do, potentially the less reliable your data may be. So it's a well-informed piece of guidance developed by industry, and we use it a lot. In saying that, some years ago we commissioned a report mindful of where industry was heading with respect to non-invasive. It's archived now, some of our research reports. Nonetheless, there's a path there from our website. But it's important to point out, again, this was commissioned by us, but not written by us. One of IMechE's stalwarts, John Wintle, contributed heavily to this. And it effectively says there are some high hazard situations where, we really have to take a step back and think we need an invasive inspection at some point in time. There's a word of caution in there, and I think it's a sensible word of caution. So question yourselves, I think, when it comes to non-invasive. Inevitably, it relies on an intelligent customer. Let me describe one example that we've come up against. This is not too far away from me. This is a storage tank of phenol, and I was riding shotgun on this inspection. A colleague was actually driving it, and I looked over the bund for this phenol tank and saw this. It's a bit difficult. The image is a little difficult to interpret, but it's basically a large vertical phenol tank, lagged, steam heated, and you may even see some steam heating through the base. It's a concrete base. The tank barely fits on the base. There's a pool of what appears to be water, but it's pink. And if I tell you that phenol leaks pink, it might describe the condition that we faced. It's an insulated tank built in 1977, and that insulation has never been removed. The duty holder was very proud of the fact that they'd adopted a non-invasive inspection regime for this tank. I questioned that, and they said they'd undertaken an RBI with a competent person. I asked to see that, and that RBI didn't recognise the corrosion under insulation threat or the potential for base corrosion, given that there were some redundant steam coils underneath. The main threat identified was from corroded holding down bolts, would you believe? And subsequent to that RBI, the same competent person inspected this tank and said, yes, it's in good order, and the holding down bolts were in good order. It didn't take long to ascertain that there are no holding down bolts on that tank. So this RBI was effectively debunked, and plainly the inspection was debunked as well. Really disappointing that it takes an HSE and a regulator visit to get people to reappraise. And there was no pushback from what should have been an intelligent customer in that instance. I also said I would talk a little bit about research. This is some research that I initiated some years ago, just prior to COVID, unfortunately, in relation to remote visual inspection. Now, the findings have yet to be published, which is slightly irritating, or I should say, is expect something hopefully towards the end of this year, early next year, published by the Energy Institute, which takes our research and adopts it as relevant good practice. But nonetheless, I can talk about some of the findings. Generally, remote visual inspection was poorer than close visual inspection in most instances. Not as successful as identifying the nature of features as close visual inspection, because RVI, remote visual, has inherent limitations. For example, oblique viewing, depth of field, lighting, obvious lighting issues, and you can't actually physically feel the surfaces. Defect sizing was variable, and some features were significantly undersized. So that's for crack-like defects. It's for diagnosing corrosion, for example, as well. And this is on multiple platforms, so including drones, but also within vessels as well. So a word of caution about techniques that we may adopt in order to avert vessel entry for humans. A little bit about lessons from other major accidents. And I was scouring the Cullen report, which is in two parts, and again, readily discoverable on the internet. And I would encourage everyone to read that and perhaps watch the BBC documentary, which is airing starting this week. But there are some lines, a line from Lord Cullen, which struck me here. And a danger that compliance takes precedence over wider safety. The major accident issue was largely taken for granted, and they thought that it couldn't happen to them. The compliance was with respect to company procedures. And in this instance, it was in relation to the divers, and the deluge system was turned off while the divers were working underneath the rig. The deluge system was never turned back on Piper Alpha, and I think pretty much without doubt contributed to the scale of the disaster and certainly the speed of it. There is, though, another part of Lord Cullen's comment there, that sound innovations are discouraged. I would agree with that, and I think some colleagues will go on to talk about AI, machine learning, etc., and what that can do for us, but also advances in NDT. And I think as a regulator, we need to be receptive to that too. I would also point people towards the Nimrod review. That might sound a little bit far-fetched, but Sir Charles Haddon-Cave gave a talk at the 25th anniversary of Piper Alpha, where he reflected on the Nimrod disasters. And there are some key lines in there, and I think Richard's already alluded to this: beware assumptions. Absolutely true. Don't assume that everything's okay, and question everything. Avoid the comfort blankets of complexity. Just because you make something more complex doesn't mean it's safer. Focus on the problem, not just compliance, and don't ignore the awkward voice. I think I'm keen in this instance to make sure that those responsible for the engineering remain responsible for it, make independent decisions, and are not browbeaten by, for example, pursuit of cost. It needs to be safe first, and then cheaper. Avoid change for change's sake. That speaks for itself. Management of change, Richard again alluded to it. It can be disruptive and highly dangerous. We, as it must have intelligent customers, and the people taking the risk must understand the risk that they're taking and be able to question the advice that they're given. There's a key phrase in Sir Charles Haddon-Cave's report, which is avoid the triumph of generalists over specialists. The specialist has the knowledge, and don't ignore them. And plainly, as equipment ages, we need greater rigor. We need potentially have to throw more resources at it and greater vigilance. So I'll try and summarize, conscious of time. With respect to non-invasive, we would expect companies in the UK and Great Britain to adopt the hoist G103. That's relevant good practice. But you need to adopt all of it. It's not a screening exercise. It's there, which asks diligent questions, it asks rigorous questions, and you have to answer all of them before you can adopt a non-invasive inspection. And briefly touching on non-invasive, it's what you can't get to think of as well. Don't dismiss what's unreachable. The tank floor, for example, in my previous example, sumps of tanks where we've had multiple failures of storage vessels, saddles on pressure vessels. Also think about what external access you may need, because removing insulation and scaffold to get to the same level of coverage and assurance can be expensive. And also the cleaning, if you're going to undertake a remote inspection, it needs to be suitably clean, and putting a person into clean is plainly not possible. Beware the capabilities of NDT. So that probability of detection, the RVI limitations are examples that I've spoken of. And we're on confined space entry. I appreciate there's an occupational risk that comes with that, but it's potentially comparable to the diver risk in Piper Alpha. Confined space entry, we've been practicing that for quite some years, and so it is reasonably practical to do it. And to pitch one against the major accident risk is not necessarily fair, I think. We can't trade those. They both need managed. Of course, it's advantageous if we avoid the confined space entry, but don't let that be the sole driver. And so any non-invasive regime has to be as good as going in. It needs to be an equivalent, ideally better, but certainly not less. And think about what invasive examination may get you. It does have fringe benefits. There are the tales of the unexpected, things which you don't expect to find when you actually go in. And I'll end, I think, by don't undermine the responsible engineers by reaching a conclusion before the review. I've seen instances where sales will knock on the door, speak to a senior manager and suggest non-invasive or different alternatives. And it undermines potentially the independent position of a responsible engineer. And we need to protect that. Finally, don't lose sight of the major accident that you're trying to prevent. Thanks for that.
Okay, thank you very much, David. Okay, next I'll invite Harry Moss on.
Thanks, Alan.
I
Hopefully you can hear me.
can hear you, Harry. I'll just bring
Excellent.
bring your slides up. So,
well, thanks for the opportunity, Alan. So I'm going to be talking about a perspective from upstream on improving safety, production, and reducing cost. So next slide, Alan. So it's unquestionable that upstream oil and gas faces increasing complexity and cost pressure, and this comes from volatile markets. So what I mean by that is the price of oil swings between $65 to $100 a barrel. There's lots of things going on in the world. The Russian invasion of Ukraine sent the oil price to a confused state. Aging infrastructure. So 80% of the production in the North Sea is by platforms which are over 50 years old from a nominal design life of 25 years. So they're beyond twice their original design life. And we have rising safety and sustainability expectations. This is clearly a good thing, but it brings a necessary cost to the business. In terms of safety and production and cost efficiency, these are the critical success factors for upstream oil and gas. And in terms of the, Alan, just thanks.
Yeah.
So what we describe as operational excellence embodies all of these three themes. So my hope here is to give you examples of where major opcos, operating companies such as Shell, BP, ADNOC, and Chevron, the ones that I've worked with, but others as well, have delivered performance improvement. Next slide, Alan. So let's begin by acknowledging some of the key upstream challenges. So I've defined these in terms of safety, production, and cost challenges. It's a long list, small print, but as I'm sure you're all aware, we've got harsh environments. This might be offshore, it might be onshore, but it's climatic challenge that makes implementation of safety difficult. We've got an environment where there are long shifts and high stress conditions. People might be working 2 on, 2 off, 4 on, 4 off. These, they're away from their family. This leads to increased stress. We've got legacy infrastructure, aging issues. The facilities built in the 1950s, 1960s were built to different safety standards. There's a lot of capital required to upgrade those to modern safety standards. We've got an increasingly complex regulatory environment. It's a good thing that the regulatory environment is continuously updating, but that leads to a necessary rethinking about safety management systems and training. There's cultural resistance, so that there's an inertia to shift from a reactive to a proactive safety culture, and that can lead to internal pushback. So in terms of production challenges, we've got reservoir variability, hugely complex subject. The national oil companies tend to have the easy to access oil locked up. So that means that the major opcos are into deep water, sour gas environments, very variable in terms of geological unpredictability, and that affects production efficiency. We've got fragmented data. So we might be talking about maintenance systems and assets management systems and integrity or inspection management databases. These databases don't necessarily integrate or talk to one another, and that hinders real-time decision making. We've got a greying of the industry. That's leading to skills gaps. There's a lack of trained personnel to pick up the new systems that are coming in and interpret the data. And we've also got slow adoption of technology. High upfront costs mean that it's necessary to build a strong business case to push it into the company. In terms of cost challenges, we've got the pricing volatility that I talked about. That has a long-term impact on budgeting and profitability. We've got supply chain disruption. We could call that Trump tariff land. So we've got global logistics issues and inflation, which drives up material and service costs. And then we've got resistance to change, that organizational inertia, which hinders the adoption of lean practices and automation. Let's just do it the way that we always have. So these are challenges that prevent the adoption of technology. Next slide, Alan. Okay, so I'm going to talk about each of these in turn. From a safety point of view, some of the technology that I'm aware of in major opcos includes drones and robotics. So these are now routinely used for flare stack inspections and robotics for undersea operations. They have the benefit that they reduce human exposure to hazardous environments. Another innovation I'm aware of is advanced monitoring systems and predictive analytics. So real-time sensors, the Internet of Things devices, bringing in AI for monitoring systems to track equipment health and predict failures. So an example might be the monitoring of choke valves using permanent installed UT sensors. That data can be married with sand production. So you can make decisions about, do we increase production, knowing that we are going to increase the erosion rates, but it's operating within an integrity operating window. We have safety management systems. So we could think about those in terms of Swiss cheese or bow tie type environments, building blocks, which can be verified and audited. We can have assurance programs. These frameworks can be driven by leadership commitment and risk assessment and support emergency preparedness. Essentially, it's the blend between integrity and process safety. And lastly, the cultural shift towards safety. So there's an increasing expectation around safety. And I've listed just a few of the things where I've seen improvements, such as training, safety briefings, hazardous awareness programs, competency-based certification, near-miss reportings. All of those are, I believe, in major companies headed in the right direction and now considering human factors, human performance issues. Next slide, Anna. Okay, in terms of increasing production, I've tried to make this slide acceptable to the non-downhole specialists. There's a huge amount of reservoir and drilling technology innovation, but perhaps that more relevant to the people on this call, it's around digital oil field technologies. So these include the blend of AI and machine learning, and Jonathan will talk more deeply about that, where reservoir modeling and production forecasting are blended together. So as you're drilling and you're taking core samples, you're matching that with seismic data. This can then lead to optimized downtime and improved recovery. So there's the integration of data. So that blend of seismic drilling and production to make smarter real-time decisions. So there can be decisions at the coal face, or rather the sand face. So digital twins are now being routinely used to optimize drilling and production operations. Routinely now, the 3D model that's used to create the project and the materials takeoffs can be taken into an inspection environment as a inspection 3D model. Another improved production point comes from optimized integrity programs. So a couple of previous speakers have talked about the use of non-intrusive inspection, which to me is a blend of specialized NDT and RBI. So it's really identifying the damage mechanism and matching it to the NDT, the specialized NDT technique. So the benefits are reduced vessel inspection, so reduced confined space entry risk. In terms of the production benefit, we might be talking about reduced mechanical activity through not entering the vessel and having to prepare it. And that leads to a reduced turnaround. So when you consider, for instance, a typical 100,000 barrel a day platform, each day that platform is not producing is a $10 million loss. So the way that in some major companies NII is talked about is to the senior executives the equivalent of bringing a new field into production. So the value is there in their mind in terms of increased production. Next slide, Alan. Okay, in terms of reducing costs, I've broken these into 3 areas. So lean operations and logistics optimization. This might be around marine fleet rationalization, the transfer of oil in tankers or gas in LNG vessels. So what has been seen by this optimization is a 20% saving through optimized scheduling and usage. There's having standardized equipment and processes, so that has resulted in a 10% variability and simplification of maintenance. So we're bringing in things like optimized sparing, for instance, not just across one asset, but across a number of different assets, or the sparing might be owned by a vendor. And then permit to work streamlining, for instance, just avoiding that waiting around for permits at the beginning of the day, doing the permits the night before, can lead to a 20% efficiency improvement through work authorization. And lastly, the use of remote operating centers. So for instance, reducing the number of people on the platform improves the process safety risk. So it's essentially operations from the beach or operations more remotely, and analysis of that data to optimize operations. Secondly, in terms of strategic procurement and electronic procurement, 3 ideas would be bulk purchasing and long-term supplier partnerships, negotiating better contracts, so long-term supply agreements, bulk purchasing to reduce procurement costs, and energy efficient measures. So optimizing fuel usage, using heat recovery around the asset, reducing flaring, which is now a greenhouse gas requirement, scope 1. And then thirdly, in terms of cost control in engineering projects, so now there's an increasing use of real-time tracking and predictive analytics to allow real-time financial oversight and reducing overruns in projects. Next slide, Alan. Okay, so let's look at what we might have as a stretch target from these 3 initiatives. Essentially, if I was running the company, that's never likely, what things would I pick from a long list of improvement opportunities? I think it would be possible, very optimistically, to have a 1-year outcome where we're looking at a 30 to 50% reduction in safety incidents. So, of course, the aspiration is 0 incidents, but realistically, we're going to have to trend incidents down on something like a Bradley curve. And so the initiatives that I'd be picking would be deployment of internet sensors, drones and robotics. I'd be trying to talk to senior management about predictive maintenance, that maturing of your maintenance practices to prevent failures, moving away from a reactive environment. I'd be pushing a safety culture, programs and incentivizing those. And lastly, looking at compliance assurance and audit and HSE training to reduce fewer incidents. Okay, next slide, Alan. Okay, if we talked about production optimization, higher recovery, I think in a half year we'd be looking at 10 to 20% increase in production efficiency. And these numbers, by the way, I haven't just invented, they are what have been seen within major opcos. Looking at perhaps in a 5-year outcome, it would be a 30% increase in production efficiency. So that my winners that I'd pick here would be AI-driven reservoir modeling and forecasting, automated drilling and wellbore accuracy tools, real-time production tuning systems, and use of NII and RBI to optimize turnaround intervals and durations. And by the way, generally in the major opcos, there was reference here to Hoy's RP 103. That is widely used globally. Next slide, Alan. Okay, in terms of cost reduction, lowering expense within the company, I think a 1-year 15 to 25% reduction in operating costs could be achieved by standardization of equipment and processes, the rationalization of spares, centralized operations via remote control centers, moving into an e-procurement platform for better pricing, and having strategic supplier partnerships and bulk procurement deals. Next slide, Alan. Okay, so many companies have been at this for a long time. There's plenty of change management lessons that we can talk about. I think if you were talking to the executives, the 3 key questions for a new process or technology comes highlighted there in red. And it's well worth reading that Energy Institute document, Guidance on Human and Organizational Factors for Implementing New Technologies. The questions are, will it be beneficial? Will it affect safety and security risks? And will it be accepted by the workforce? So what I've set out here are 4 phases. The adoption of technology by major operating companies doesn't happen quickly. It's not a flash in the pan. It needs to be planned. So at phase 1, we're talking about assessment and planning of a program. Maybe in phase 2, running a pilot at one site. Phase 3, deploying it fully across the company over all of the sites. And then phase 4, it's about monitoring and optimization and sustainability. So without buy-in, these programs are doomed to failure. So the 4 bullet points I've got at the bottom here are about how do we get the buy-in of the management and the workforce. Well, it's internal campaigns to promote innovation. It's about leadership championing the new technology. So clearly there has to be a perceived benefit and a business case presented to them. Having transparent communication channels, whatever that is across the company, and celebrating success and wins, and having incentives for adoption and feedback loops to show that things are being achieved. And these are the ways, I think, that we change the culture or transform the culture to accepting innovation. So I hope that's given you a quick view of an upstream perspective. Back to you, Alan.
Sorry, I was on mute there. Thanks very much, Harry. And I'd like to thank Harry because he's on his holidays. Right, so our next presenter is Jonathan Lowe. So, Johnny, do you want to put your slides up? Okay, Johnny's going to talk about AI and asset integrity. Over to you.
Hello, thanks everyone for getting on the call, taking time out of your day to listen to all the presentations so far, and thank you for all the speakers so far. I know we don't have infinite amount of time, and so I'll start off by giving a brief introduction, telling you what we're going to talk about, and then going through it. I think my talk today will be quite different from other speakers. We've heard a lot about sort of interesting developments and how to improve process safety in plants. And what I'd like to talk about is AI. And I'll start off by trying to condense several hundred or if not thousands of papers published over the last 4 years into a 15-minute session. So wish me luck. And explain the application to asset integrity and into industry in general. So I'm Johnny. I'm one of the co-founders of a company called Scope. I don't come from an industrial inspection background. I used to work for a fairly small company called Google, a spin out of it. And yeah, we've been lucky enough to grow massively. We work with major oil and gas players, major inspection service providers to speed up and help them better capture data in the field from industrial inspection and maintenance work. And it's exciting what we've learned over the past 2 years. I think I've been on 20 different sites. I've done a ridiculous amount of training courses and confined space entry, and I've lost my PP at least 3 times on different trains. And so it's been really interesting to see. It's essentially what is a new world for me with my AI background and expertise, and to learn about opportunities for improvement in the space. So what will we cover today? I'll try and be on time. Things that we'll talk about will be like how language models work. So language models are a new type of AI model that have been developed sort of over the past 5 years. Most things that you will have seen in the news over the past 5 years relates to them. We'll be talking about how things have changed. I'll be talking about 2 to 3 applications, depending on how much time we have, of applications to industry now. And to talk about some sort of risks and considerations you should keep in mind when using these models. Things that we won't really cover, historical ML models. We won't go deep into the technical details. We won't spend time talking about the mathematics or implementation of how these things work, although it's like really interesting, and I'll more than happy to answer any questions or get on calls with people to talk about any of those things or how we've seen them in different plants or different customers. And then finally, ethical or other concerns. There are many, and there's good space and a lot has been written, but we just don't have enough time to cover it today. Great. I'll also be happy to take questions at the end, as with everyone else. So I would first like to just spend a little bit of time talking about something that I get to see a lot, but I think people who are unfamiliar with AI don't get to see as much. And that has sort of been the insane progression over the last 3 to 4 years of language models. And so I'll talk about how they work in a second, but I'd like to give some examples. So on one side of the screen, we have a model that was released 3 years ago. It's DALL-E 1. It was released by OpenAI. And at the time, this was sort of the state of art of image processing. I think it was something like, Heisenberg from Breaking Bad mixed with some cat. You see that it doesn't do placements that well. You'll see that images are sort of blurry and it's not as high quality. And then on the right is one that I generated yesterday. I had like a really short prompt. I just said, some text that relates to IMechE in front of a futuristic, cyberpunk background. And that was it. And you can go to many image generation models now if you like. There's one called VO3, just came out from Google, and literally try the same prompt, and you'll be able to get a sort of similar answer. And so you're seeing this like insane development. This is literally 3 years of time. And the results could not be more different. And in many senses, there's also been sort of a watershed moment for AI in general in the industry where we've seen investment levels rocketing from what was historically between 1 to 10 billion circa per annum to between 50 to 500 billion dollars. We've seen companies like OpenAI go from valuation of $10 billion to $500 billion. And companies deploy real money in building massive data centers around the world to essentially train and make these models better. What else has improved? We're seeing that models are improving. And actually, in some sense, when you plot performance, you see hyper exponential performance increase, which is kind of scary. It means that models are not improving only at an exponential rate across most benchmarks, but at a hyper exponential rate. And there's some different reasons behind that, but many people think it's because models can help generate training data for the next set of training. The better the model is, the better the training data. And so you don't only multiply itself by itself, which leads to an exponential growth, but you get to do that a couple of times because there's a couple of inputs that relate on this. And so you get sort of this hyper exponential improvement. In this case, the front chart that I'm showing is a set of math problems that they essentially brought together the world's best math professors, asked them to come up with difficult problems that only they could tell. I've released a benchmark a year ago. You can see most models were at sort of 0%. Over the course of that time, we've gone up to 28 to 30% just within 1 year. And we've got other benchmarks. This is from January 2019. How long can models perform? So GPT-2, which was sort of one of the first models, could really only do tasks for about 1 minute. And now we've sort of got extended tasks, can carry out the same work for over 2 hours. So maybe that's doing some sort of research project or so on. And so models are getting like significantly better. There's a really good resource on this if you want to look into the sources that I have behind this by a company called IMechE AI. They publish a lot of really interesting data. And so models are getting a lot better. There's like wide ranges on outcomes. It's not going to tell you that things are 100% accurate, but in general, on core benchmarks, models seem to perform better and better these days. How do these models work? It's a crash course into them. So historical models worked by taking very specific set of data. So maybe you had a set of ultra thickness readings for different pieces of equipment over time. And then you would do something like a linear regression. So that means you're essentially plotting the data on a graph, and you're trying to work out, what is the thickness next going to be over time by mapping a line that essentially best approximates that set of data. That works really well for one piece of equipment and some measurements over time. But if you instantly try and take that information and then transfer it over to even a different piece of equipment, or you're doing some stuff with radiography instead, or different sort of measurements, it's not going to work at all. And so models work quite well, but they're really localized to specific tasks. And that's quite different to the models that we see today. They're called large language models because they're essentially trained on all of the internet, all of human knowledge, on answers of PhDs. They spend like hours just talking to the models and improving them. And all of that training essentially improves the model and helps it sort of build its own worldview. This is what we call it, some sort of next token predictor when you give it sort of the world as a predicate. And so how do the models work themselves? There's a fancy word called autoregressive models. And so to sort of break down the etymology of it, it just means that they work by automatically using the history. So that's the regression of what they use. So they use all of this previous words. I don't know if I can write on the screen, as the context. So maybe you'll start with where are, and then you'll try and predict the next word, and then you'll get the answer of the next word, and you'll use it to predict it. And by using this historical information and doing this training not across just sort of one sentence, but across billions of tokens, and so the largest models are trained on at this point between several hundred billion and trillions of tokens. Models can actually build up some understanding of the world. And so if you ask them to complete tasks, or just talk to ChatGPT, this is how it answers your questions. Which is why if you interrupt it, or if you swap out words in the middle of a sentence, you can get quite interesting or funny responses. And this sort of brings the intelligence to the model. So if people ask, well, how does that actually work? This is, and there's interesting studies. Different people can show, well, maybe you just think, well, it's not actually got any intelligence, it's just predicting the next word. But when people take the models apart, certain sections of them, and they do interesting interpretability things, you can predict, you can essentially construct rules that they have internally about the world that mirror the actual, physical rules. So, for example, you get it to predict some sequence in a set of games. So maybe you're playing Monopoly or Othello or something like this, and then you ask the model to do it. You can see that the rules are the same, and so it's actually constructing a viable representation of the world. And it's, yeah, I don't try to anthropomorphize these models, but in its brain, or in the model itself. And so that's quite interesting. It means that these models can now do new things that they weren't previously able to do. And so that's like really exciting for industry. And I think actually I wish a lot more people thought about this and a lot more people read about it. I think there's been like big growth, and I'll talk about this a little bit at the end of my talk. There's been big growth in sort of regulatory pressure and costs, and we've got a lot more learnings than before. We've got a lot more experience than before, but we've also got less people, less money, and so I think technology can really be a lever to use that expertise more efficiently. And to be honest, I don't know, maybe we'll just ask around in your plant or in other places. There's just really not that many people thinking about how to use modern technology, really modern technology developed in the last 5 years to make assets safer and to make them more efficient and so on. And so this is a lot of what I spend my time thinking about, and a lot of what we help our customers with. How do we take these models, which can also be false, this is not 100% accurate, they're non-deterministic, and apply them to high hazard, high risk industry. Like many of you work in coma sites, many of you work in places where you can't even take phones on site. How do you square these two things together? How do you square this growth of intelligence and this really useful tool with the industry that you're working in? And maybe you've got different answers, but I would say, like, my big takeaway has been, don't pass on decision making to models. I think this is a big mistake, and I'm always really I always really wonder how companies work when they just try and pass on a lot of this decision making to models. But instead, I would try and use language models to augment human decision making, to help people through training, through information gathering, through keeping the information up to date, and through a bunch of use cases which I'm going to talk through. So yeah, this is just important to keep in mind I would really not recommend. I think models are just really just not at the stage of intelligence, slash like, most models are not configured to be able to add evidence correctly, to be able to outsource decision making, but they are in a place where they can really improve decision making. And I think if you use them properly, it can be really useful. And I know there's like a lot of skeptics, but I would also just really encourage people to just try and play with them themselves. As part of my advice at the end of the talk. So, what sort of applications do I have, or ways that we see this work well? And so I'm going to talk about two main things, and I think we won't have time to get a third. And the first is information retrieval. And so language models are really good at searching for things because of the way that they're trained. Over some long document depth, they can find really specific pieces of information. And so they did this test that's called a needle in a haystack test. And so you sort of got incredibly accurate results up to about 64,000 tokens, which is, maybe 2 or 3 fairly long books. And it's interesting how this sort of mirrors human knowledge, often at the beginning, sort of at the beginning of books, or you'll read the first couple pages, you'll maybe miss the beginning, you'll sort of remember a lot of towards the end. But we run these tests on models all the time where we put in one really specific fact. We'll keep everything the same, but we'll change one sentence in the whole book. And then we'll ask models to tell us, what sentence has been changed. And I wonder if you were able to do this, if I gave you some Book of War and Peace and I changed one sentence within it and I said, okay, you've read it twice now, which sentence changed? Would you be able to like accurately tell me where and how the sentence was changed? I think it's like pretty difficult. But models are able to do it pretty well. And so that's sort of the first use case. Models are really good, and especially if they're sort of developed correctly, there's a lot of applications here. And so what are some of the applications that we've got? Is what we call like data ingestion or information retrieval of that data that's been ingested. And so, for example, you can ingest in documents like P&IDs, process and instrumentation diagrams. If you're working with, hundreds of these and you've ever done sort of a risk-based inspection study before, you know how time-consuming it is to go through and find every single piece of information. Instead, what we recommend is using models to find that piece of information and humans to validate it. And so maybe it'll give you a line number and it'll give you a small picture of where that line is and would link back to a source document, and you can physically verify the information. Other things it's really good at is scanning in and summarizing inspections. So if you're planning a shutdown, you can see what inspections are outstanding, what ones you need to work on. You can take in quite complicated diagrams. Models are getting better and better at this all the time. There's not many off-the-shelf models that can do it, but if you sort of tweak them and do some interesting things, you can take in, words in different languages. Maybe, you've shipped over a new catalytic converter from a different country, and you want to use that, but the GA and its manufacturing records in a different language, you can use these models to do pretty accurate translation of that information. Again, I'll just encourage you to use humans to verify sort of key aspects as you go along the process. In fact, I would almost say that's necessary. In none of our tools we have, essential sign off without humans. Humans are part of every step, and we think it's really important to have, SIEs, responsible engineers, checking over all the pieces of information. But it's much easier to verify information. It's sort of a good principle of cryptography than it is to find it. If I asked you, find me this specific line again in War and Peace, you probably find it really hard. But if I showed you that specific line and I said, does this person say this fact? And you can see it on the screen, then you can say, yeah, I can see it. I can see the reference to the book on the page. And so this is what we try and do, to replace fact finding with fact verification. And this is really useful. It means that a lot of things that were previously just on PDFs or scanned or in your basement, you can now digitize. More than happy to talk to you how we've seen people do this and how it works in practice. But yeah, you can save a lot of time and a lot of energy. Yeah, and then you can bring information together from other places. Models are like quite intelligent at understanding, and doing sort of multi-shot classification. So if you've got many different buckets, classifying things into different buckets used to be a hard machine learning task. These models are pretty good at doing it, and so they can put, sensor information and PNID information and inspection information all about the same equipment at the same place, and so you can end up with one source of truth. And so I think this is quite an interesting use case. I would hazard that, I'd say maybe that when I've gone to sites and I've asked, I pointed at a piece of equipment, I said, tell me everything, tell me the design pressure of this piece of equipment, or, provide me the documentation about it. Most people would take, 2 days or 1 to 2 days to find the documentation about it, because we're generally not good at, doing information retrieval on a large set of information. And I think with the help of AI, we can now get a lot better at this. So this is sort of one use case I think people should be thinking a lot more about, and ties directly into asset integrity because, like sort of Alan said at the beginning, there's just a lack of large visibility about what's going on at what stage in different places and different plants. And this can really help with that visibility if you do it right. And so,
apologies, Jonathan, 4 more minutes, just so we can finish. Go on.
All right, I'll wrap up quickly. Okay. There's an example of a small task we did here with Tube Island where we set up and ingested a lot of data points, and so essentially they could predict or use AI to suggest damage mechanisms against certain pieces of equipment. I think another really quite cool use case is information generation and guidance in the field. And sort of a large application here is like report generation of inspection reports, but also maintenance reports. Sort of a key here is to generate information sequentially with approval. And so you never ask a model to generate the whole report for you, or, you never ask it even to generate, big chunks. You just say, generate small sentences here and here, get humans to approve them, get humans to edit them. Otherwise, you can ingest standards and written schemes of examination to ensure accuracy in the field. And you can also have models are really good at taking in lots of different sorts of input. Historically, it was just text, but now they can take in audio and video, and they can, most models that are trained these days are trained on a variety of input. So I'm pretty confident that Google's latest model was just trained on all of YouTube, for example, and probably on a lot of your emails. And so having all of that context means that they can really understand what videos are like. And so, yeah, large application here being you can save hours if you set it up in the correct way on manual report writing. You can automatically catch some simple errors in the field. If you're taking information in, models can say, lengths can't be negative, or, flag a warning up if thickness has increased, when you're doing some CML readings or so on. And I guess this was just some sort of large point that I wanted to make to finish off, sort of thinking about one of the previous talks. We were thinking, well, technology is not always better. For example, remote visual inspection doesn't work as well as closed visual inspection. But at the same time, we've got less people to do closed visual inspection. Many people in the industry are retiring. But at the same time, there's much more regulation. There's much more learning. There's less funding and less resource. And so I would sort of challenge people to think about, like, how can you use technology as a lever against these things? Technology is useful because you can copy and paste things, and so programs scale very nicely. And so, how can you give people more training, more guidance in the field when they're doing their work with technology? How do you give them the right section of written schemes to make sure that they're doing the inspection correctly? And how do you, partner with technology providers to improve the asset integrity on your plant? I think it's really just worth thinking about. Maybe your answer, you'll walk away and you say, actually, I don't see any application for the work that we do today, and that's okay. But I think if you're not thinking about it, you're missing out on a big trick. And so I'd really encourage you to do that. There's some risks, and they're sort of highlighted here. I would recommend, like I've sort of said many times, make sure the data leads to bad decisions. Make sure that your data is okay. You're reading through it manually, that it goes into the model as well. And sort of just the takeaway point, some homework, some, thing to try. There's a really cool tool that I quite like using a lot. It's called Lovable. It's free to sign up. They give you some sort of amount of credits. And if you've ever wanted like a personal website, or you've ever wanted, like a calculator that does some sort of things for you, it's really good at doing those. So I'd just go online and I'll try it out. or yeah, and it is quite cool. But yeah, I don't own it. I don't have any shares in it, so there's no commercial interest there. But I think it's just like quite a cool tool. If we would want to try using AI and seeing what it can do. But yeah, thank you so much. And yeah, feel free to contact me or yeah, reach out to just think about AI. Thank you so much.
Okay. All right. Thanks very much, Johnny. Okay. All right. The last presentation will be John Wiggins. If I can ask John to put his slides up.
And just Alan, while you're just talking and,
Yeah.
and he's putting his slides up, I'm recording the webinar, but I won't stop it directly at 1 p.m. because it's an important webinar. We need to allow the topics to run out, and we are running a bit late. So,
Yeah.
I will carry on for a few minutes. So make sure we get through the topics correctly.
All right. Okay. All right. Thanks very much, Richard. All right, John, over to you.
Thank you, Alan. Thank you, everyone. So, a bit about your host. I have over 20 years' experience in the design and construction of machinery and automation systems, primarily working for OEMs and utility companies, but many others in between. My name is John Wiggins. I am the Functional Safety and Cybersecurity Technical Manager for DECRA. For those that have never heard of DECRA, the company is a German company which has been around for 100 years. We are one of the global leaders in safety consultancy in the fields of automation, process industry, and many others. DECRA provides process safety assessments, HAZOPs, LOPAs, functional safety design, chemical reaction and vent sizing assessment, battery testing, ATEX and DESIR assessment, certification, and organisation and cultural assessment as well. The talk today is based on a piece of work done by the Safety and Reliability Group, achieving reliability through the design process. Much of what we've heard from previous speakers, especially in terms of issues that have been found, many of those will stem from poor design, and this really starts at the very beginning. WG1 is, for background, is a cross-industry group, and much of what you'll see today has been derived by people who are not directly in the process industry. So we have got examples from other parts, other industries, other sectors, where things have gone wrong and things have gone right. So where do we start? We start with the classic iron triangle. You can have it good, you can have it fast, or you can have it cheap. In fact, you can have two of those, but not all three. The general balance is we want it as good as it needs to be so we can have it as quickly and cheaply as possible. But where does reliability and integrity sit in that? Should it be considered when you're planning? Unfortunately, usually it's not. It's usually the thing that's sacrificed. It is either forgotten or deliberately sacrificed to try and get a design, a project done. But what can be done to minimise this? The first stage, and I thank the Royal Institute of Chartered Surveyors for this diagram, is that you should consider whole life cost and consider an asset as not just being to the next stage, but being something that's going to be in service 20, 30, 40, 50 years. What is the cost now of decisions now that you will later have to live with? Remember that downtime is not just breaking down. Downtime is the time you need to take a plant down for inspection, the time you need to take a plant down for your maintenance, be that planned or reactive. It is everything: time for setting, time for changes, time for adjustment. Also consider a commonly lost one here is knowledge. When at the start all our knowledge is fresh and we know It's fresh in our minds. We know it. What about in 10 years' time, 20 years' time? Where's the knowledge sit then? And knowledge has been a key theme in this discussion. Much of the knowledge is lost over time. How do we maintain knowledge? And finally, environmental cost of what we're doing. Plants don't live forever. Nothing does, unfortunately. You know, they're going to have to be disposed of. And today, abandonment is not a common practice. It is still done in some cases, but we have to consider the environmental cost in the future. We also have to consider that, you know, amongst many legislations, environmental legislation is one of the quickest changing, and we are tightening our environmental legislation. So we have to think, okay, it might be good now, but what about in a few years' time? This brings us to the management of risk. It's common in project management to just look at the next, you know, the here and now. What's in front of us now? What can we do about the risk that's in front of us? We're quite poor at looking at future risk and where are we in the future. We must, when we look at the future, we must look at what we can reasonably foresee. Now, this is quite difficult and is a form of, in many cases, guesswork, but the cost of not doing it is always greater than the cost of doing it. So we should take a more holistic view and look at not just now, but the implication of what's potentially going to happen in the future. How do we do this? Well, one way is the key thing is to have a process. This isn't just good project practice. This isn't just good engineering practice. This is good business practice. Having processes and using them. A process allows you to look at, okay, these are the stages. This is what's going to happen in the future. And we can start to build a framework of, okay, this is what is likely to be needed at each of those stages. We can start to look at the big blocks of future planning. You can look at the physical requirements that generates, the organizational requirements, the human factors, and the competency requirements you are going to need, not just now, but in 10 years' time. A process, whilst it does not ensure reliability in itself, is a reliability enabler. It is the fundamental reliability enabler. If you don't have a process, you know, as the old saying goes, if you fail to plan, you plan to fail. And not having a process is a failure to plan. So what happens when the future is not necessarily considered? And I use quite a potentially contentious example of the Type 45. These ships aren't necessarily actually unreliable. They're just unavailable. What do we mean? Type 45 currently, only 2 out of the 6 Type 45s are in service, right, as of the last report. Type 45 has been plagued with availability issues, typically being 45% or less. These issues stem from fundamental decisions made in the design phase. The impact has been huge and is ongoing. There are Type 45s that have now spent longer in dry dock than they have at sea. And the process to repair them actually it requires a dry dock period longer than their construction. This is, you know, cutting holes in the sides of ships is never something someone does without good planning. So what happened? Well, all the factors in the operation of the ship were not considered, but, you know, certainly from the articles that have been published on this, different climates weren't fully considered. The fact that the ships are going to need to be updated, that was considered, but considered as secondary to the operating requirements for the ships and getting the ships in on budget. So the short term was prioritized over the long term. And what's the impact? Well, if we look at this, a very nice graph from Gibson Hamilton really shows it. At the front, you have maximum influence and minimum cost. At the back end, you have minimum influence maximum cost. A good guide is that a decision made in the concept design phases will cost 10 times as much to correct by the time you get to construction. And that is quite staggering. So a £10, a £1 million decision now is a £10 million decision in the future. So how do we assure this? Well, we need to quantify what we want. Fundamentally, we must quantify our decisions. We must quantify that what we're going to do it, how it's going to do it, and what our availability requirements are. You notice I use the word availability, not reliability. We need to quantify how long we want this thing in service for. That includes downtime, that includes setting, that includes inspection, that includes adjustment. It is everything. Consider that procurement is a form of downtime. If you're waiting on a spare part, the machine is down. And yes, not just hardware, we're all good mechanical engineers, but software as well is critical in this process. Once you have that framework, make sure you've got a strategy in place for it, for that system. At the very beginning, how am I going to maintain it? Benchmark it. Is that achievable? Does the technology exist? Do we need novel technology? Can we look somewhere else? And finally, how are we going to communicate this, not just now, but communicate it into the future? How can we sustain this strategy past the initial deployment? So, reliability and risk analysis, this has been around for many years. We can measure things, we can model things, we can change things. These are based on assumptions, but like we said, the cost, these assumptions can be checked. Do your basics, do your modelling. The results can be surprising, and a good example of this is the high-speed train. We're all well aware of this in the UK. A very successful unit with a hidden secret. They knew it had reliability issues at day one. What did they do? They thought around the problem and said, well, if we put the power cars at each end and have separate power cars, if a power car fails, the other one, A, can rescue it, and B, we can just change one power car. The previous solution would have been to put both engines into two power cars, into one power car. One engine fails, the whole power car's out. So they understood the failure modes and understood the impact on the service, the impact on safety, the impact on British Rail, as it was then's reputation. Today, we add the extra factor of security in. We're in a connected world. We must look at the impact of failure on our security. Can a failure be detected? Can it be repaired? If not, what do we do about it? Is it critical? What is the criticality of that failure? Understand those factors. And finally, test it. Test it, test it, test it. You've made an assumption, test your assumption. What if it fails? What's been done elsewhere? Can we physically verify it, or do we have to do a field trial? Look at how an assumption can be verified. A good example of this and of using something from another field is PAC-SCAN for cooling towers. This is something I was made aware of through a member of this group. The technology is, the idea is to prevent people entering harsh environments. So we can monitor, we can reduce downtime, we haven't got to take the cooling tower out of service. And we use two well-established technologies in new environments. The result, we can extend PPM hugely, increasing availability for the use of some actually quite well-known technology in different fields. Why is but a plant will always fail? Why is that important? Well, unfortunately, failure is a fact of life. Failure is a fact of operating machinery. Whilst it is an annoyance, a nuisance, it's also data. We must make sure that we have the means in the system when we design it that when it does fail, We understand, we can record it, analyze it, correct it. This is the most basic form of learning, but it is so often forgotten when we are designing a plant. Another area that's widely forgotten is our supply chain. When we're specifying equipment, we specify it to suppliers. The most common failure is a failure of specification to that supplier, because we assume that the supplier knows what we know. They do not. They do not usually know anything. We're the expert. We need to make sure what we're telling them is the complete story and document this. Make sure they've got everything they need to do their job. Be sure that is a very key failure point in this chain. And
2 minutes, John, please.
I know.
Okay.
Identify, manage, and monitor. This is a Deming cycle. So when we look at management of change, we need to make sure we've got a process to change. That process is in place, it's known, and it's checked. Finally, a very good example of good learning. And it's a surprising one. It's a supersonic car. Richard Noble learned from the people who went before him. He literally interviewed the people who went before him. And what he learned was that a supersonic car spends 90% of its time plus being maintained. That these world record cars are usually being maintained. So when he designed SSC, he designed it to be maintained. In his books and in his own speeches, he actually puts that as a key factor in the success of Thrust SSC was that they could turn it around quickly, they could maintain it quickly. And he looked at the human capital who had gone before him and the lessons that they had learned. The structural capital, Thrust 2, gave them loads of data. And finally, though not perhaps quite so important, the customer capital, what did the people around him want to see? He learned from the errors and learned. So in conclusion, start early, plan for success, plan to maintain. If we don't do it, it will be multiplied. Consider whole life costs, not just the immediate in front of you. Accept that change is a constant. Things will always change. B, make sure our processes are constant. Learn from successes, errors, both your own and others. With that, thank you very much, and I hand you back to Alan.
All right, thanks very much, John. Okay, so I think I've got about 3 slides to wrap up, and then we would like some questions and answer time as well. So let me just put the screen back up. So some fantastic input from all the speakers in there, and to give a balanced view of what the opportunities are to both improve safety, increase production, and to reduce cost around asset integrity. So what you can see in this photo is the Teesside skyline. So this photograph was provided care of the Tees Valley Combined Authority, and one of the aims we're trying to do is keep as many of these facilities as you can see in that Tees Valley Tees skyline operating. So make sure across Europe we can keep our chemicals, petrochemicals, and refining as competitive as possible in there. That's what we're trying to do. So the call for action around the JIP. So we've had this initial webinar. We want to actually get as much of industry together to say, yes, we can do something. You've seen lots of different inputs, both from a process safety perspective, from an AI perspective of what's possible in there, and then bring a small team to look at how we articulate this change. What is the competence we've got at the moment? We heard a lot about the skills shortage. I think Richard talked about the loss of skills in the industry and so on, understand what that gap is, but also what's that value gap? You saw in the North Sea, we understood what a value gap, what's that value gap across our industry? Because that would also tell you what the investment potential is around making this happen in there, and then formulating a way forward. Do this under the umbrella of the IMechE and supported by IMechE. So you'll have seen IMechE slide, a logo on this, and that ensures it's open to everyone. We're not doing it from a competitive perspective. We're trying to keep everyone on board. As we sit at the moment, more than 80% of our pressure vessel inspections are invasive. require people to go into vessels, and you've heard both sides of the debate on that. The technologies that Jonathan Lowe talked about, a lot of that isn't in practice at all around our high hazard process industries. What's the impact of bringing that? Often there is no RBI. You know, if we are gonna transition, we do need to have a good RBI in there, and it needs to be properly applied in there, so we do understand degradation mechanisms in there, and we understand what technologies are available and we utilize it. Harry's presentation was interesting. He gave the upstream model. The benefit upstream half the downstream. One, the benefits are higher, but also there's a higher concentration. You've got the big oil companies in upstream, BP, Shell, Chevron, and so on. In downstream, we have a very fragmented operator base in there. So we don't have that sort of concentration, and we don't have that a level of spend in R&D from an asset integrity perspective. So that's what we want to try and do as the IMechE through this. So fantastic. Just recap on the speakers who spoke. Really a big thank you to all of them donated their time in there to give us this balanced view in there. So I've called this reimagine asset integrity. What's actually achievable? And care of Two for Ireland, I've taken 3 case studies where we've actually assessed vessels, and this has been done over a number of years in there. And you can see there is a high percentage we can transition. And if you go back to my previous slide, 80% of what we do at the moment is going inside equipment. And I do also, we need to do this safely, and we need to ensure we take the learning from any failures of the past or any way the process has gone. But this isn't just about non-intrusive, it's also about the AI technologies and other advanced technologies where we can reduce the turnaround size, and we can do inspection online as well in there. But the potential is high if we can make it safe and if we can make it work. And you saw in case number 2, which was the European and refineries, and across Europe, it's a lot more prescriptive than the UK. So it's not as David Glass described. In Europe, it's more prescriptive around having to go inside equipment, having to pressure test and so on. But these are the sort of KPIs that were delivered across the study that we conducted as Two for Ireland. And we've changed some of the percentages, so we're not sharing customer data out. But you know, the main one was to make sure we eliminated unplanned outages. But there's lots of potential to actually reduce turnaround size, reduce turnaround duration. That reduces major accident hazards, and also it reduces costs at the same time, and takes out very complex events in there. So that's what we want to try and do as the IMechE, and hopefully do it together as an industry in there. So what are the next steps? So this webinar will go online. So we're in the next 2 weeks, we'll have a recording of this. We'll ask, and there'll be 2 poll questions coming up, is to pull together a core team to support this. Hopefully some of the panel members will be part of that core team in there, and we'll develop a term of reference for the JIP, objectives, schedule and deliverables in there. We do have a face-to-face event on the 19th and 20th of November. So there is a QR code for that, as you can see on the right-hand side. But the aim is to actually get the movers across on the top from this perspective of how we can actually improve asset integrity together. Okay, so sorry, there should have been, hold on, let me just see if I can make this work now.
Technology is a wonderful thing, except when it don't work.
It's worked all the way through. I was going to say, let's see the last one, because the last one's important. If this doesn't work, we're going to have to do it through the questions and answers in Teams.
Well, I mean, the other thing is, and we can just go through some of the Q&A while you get that working in the background. So we'll do that. So yes, I think there's been pretty lively discussion in the Q&A and the chat. I just picked up, I think there's sort of 3 unanswered questions. I'm not sure quite who to field them at. I'm going to maybe start with the first one, which was Stanislav McDonald. Is vibration related fatigue a common issue relative to other types of integrity risks. David, I mean, do you see any events or incidents that come from vibration-related fatigue commonly?
In our sector, I would suggest less so, and we're largely dominated by corrosion.
Yeah.
That's not to say they don't happen, but in other sectors, yes, particularly where there's moving machinery and, for example, our fairground colleagues have a lot of trouble with fatigue. But generally, we're largely dominated by corrosion, I would say.
I will. I haven't got the reference at the moment, but if you haven't used high-speed cameras before for vibration issues, the sort of amplification techniques, they're fantastic for dealing with hidden vibration issues. If you don't know about that, or you want to know more a bit about it, I'm not an expert, but I know someone who is. So just send me an email afterwards. Second thing from Jason M. With remote inspection, if we see an issue, a risk assessment and planning for a visual inspection must be done, clearly. Is that a common approach should we apply across the whole industry? So in other words, we see if there's anything in a remote inspection, you have to stop it and move on to a physical one. Still looking at David again.
We've seen this in a few instances, and it provoked quite a challenge. For example, a vessel which is entered remotely, who discover a defect on screen, or what might be a defect on screen, and then the argument ensues. And I've had differences of opinion as to what's on the screen compared to operators. We would generally ask, for example, there was one instance of what we thought may be a crack in a vessel. Is the option to go in, or is the option to unclad at that point in time, use NDT from the outside and determine if the crack actually exists or not? I think there's generally findings have to be pursued until there's a reasonable amount of certainty that you don't have the defect. How you do that depends on what you find.
Okay, and just jumping back to the vibration question, Harry chipped in on the chat. That there's vibration and small bore fatigue are common in upstream, especially in compressors, and the Energy Institute has guidance available about that. Again, if you want more information about that, talk to Harry, or even talk to me. I'm a fellow of the Energy Institute as well as the IMechE. And then the final one that I think is not answered out of the chat, from Graham Horton: does the chemical being stored have any prohibition on the use of non-intrusive inspections?
I can speak for Great Britain then, in terms of its legislation, and perhaps reiterate the slides. It's generally a goal-setting regime that we have. We don't dictate generally how something should be done, but point to relevant guidance. So, for example, we have our own chlorine covenant. We have Eurochlor on our GEST guidance for chlorine. There's ammonia guidance. There's often guidance which is substance specific, which we would then point to as the benchmark. And if that substance or storage of that and processing of that substance dictates or guidance suggests that you should follow an intrusive path, then that's what we would adopt as the benchmark. But that's guidance.
I just throw in as well. I mean, my company's a member of Eurochlor. Almost every year they run online training, 11 two-hour sessions for Eurochlor members on safety and technology of chlorine handling. And I hope more trade associations and even EMU and other people start to think about doing things like that, because it's brilliant. I mean, there were other questions I think they've sort of been muttered about during the chat and sort of answered. Alan, you've obviously had time to fix your problems.
My problems have been fixed, and thanks for that, Richard. So we put the question on on the screen now. What are the key barriers to improving safety, increasing production, reducing costs for deployment of new technologies and practices? So we've had a number of responses already in there: budget, cost, resources, competency, knowledge, willingness to change, and so on. And maybe this needs to be compared to the previous one around the Formula One and the wanting to win and so on. In there, I do think a lot of people on top don't see the overall the cost of asset integrity because it's in many different budgets as well. But that's given us a good number of responses. So there's one last poll question then. Would you like to be involved or to contribute to the JIP? You know, if you could please add your name and company. This at the moment, all contributions are time contributions. So we're not talking about money at all at the moment. We're talking about something where we bring the right expertise together and help move industry forward so we can take advantage in a safe manner of advanced technologies and utilize those technologies to operate more safely, but also operate more efficiently and at reduced cost. So that's what we'd like to do. There are challenges, and you've heard lots of the challenges from Richard's presentation at the start, David's presentation as well, which talks about a lot of the challenges, especially from process safety, maybe from where NII hasn't been so successful. So let's learn from those, and let's see how we can actually make this work.
And Alan, I know I'm always chatting, but I'll chip in as well. So although I talked about process safety today, I hate turnarounds, and one company I was in, we used to have 2 1 hour. When I joined, had 2 1 week turnarounds per year. I moved that to 1 every 4 years, and I was moving it to 1 every 5 years. It's not impossible, and I'm quite happy to tell people how we did it. It's not easy, but when you think of the huge impact on costs and output of a turnaround, if you can avoid them safely, it's well worth the journey.
I agree with you, Richard. I spent 4 years of my life working in turnaround group. Then I came back and managed to turn around on a refinery, and I would say it's the best time of my life managing turnarounds from the power you hold, your ability to make things happen and so on. But I also think, we did hurt in the ICI days. We did hurt people. We sent someone into a nitrogen receiver, an inspector into a nitrogen receiver in a turnaround. I did hear a story in Saudi in the last few years where they had multiple fatalities inside a vessel that was in the turnaround. I also understand what David said, that we can make invasive work, but I think invasive comes at a high cost as well. So making turnarounds smaller reduces risk, I think. And if we can do that in a smart way without impacting on process safety and our ability to manage asset integrity on assets, we should be doing that. And that's the viability of keeping our plants running.
But that needs those competent, experienced, trained experts, and that's where I will bang my drum about that, and I'll continue to do that. And if anybody's interested, by the way, I know we're just waiting for these things to come up. HazardX in Ellesmere Port, I'll be talking about safety critical task analysis, which is something that is really important and linked to that. And then TUV have also got a PSM conference a week later as well, where some of these topics will be reiterated and dusted off yet again.
And what I would like to see as well, Richard, and I don't know how many people left in the audience, I spend a lot of my time working in upstream. Upstream is much more collaborative than downstream. I'd like to see the same level of collaboration in downstream as you see in upstream, especially upstream Aberdeen. The other thing is upstream Aberdeen has a much louder voice than downstream. Maybe Miliband's changing that at the moment, but they we talked about the work we did with the Oil and Gas Technology Centre. They're much better at being able to get money from government and to do research that's collaborative and to change things how they are. I'd like to see us do that downstream. So we counter what was on the INEOS website about the extinction of the chemical industry in Europe. How can we get the chemical industry working together to actually ensure it survives and it flourishes in Europe?
I mean, just in my own company, Westlake, we're currently shutting 2 sites, one in Europe, in the Netherlands, and one in China, and we're not the only ones.
Okay. Some people have written yes here, but it says anonymous. So if you can put your name, at least we'll know who you are, please. So we will have a list of the attendees, but if you can put your name, because anonymous might be hard. Okay, let me move on. Is there any last questions people would like to put into chat for any of the panel members in there?
Or
A big
or
thank
even
you.
put your hands up, because we can always unmute you if it's
Okay.
something you really want to talk about.
All right, while they're doing that, I'll just go to the last slides and we'll come back to this then. So webinar recording. So all our previous webinars are on the website in there, so you can access this. We'll put this on the website. Might try and put 2 versions of this, put the full version and then put a truncated version in, so it's easier for people to watch because of the length in there. I mentioned during this session, there is another webinar on the 9th of September around asset performance management with looking at condition monitoring solutions. So that touches on a lot of the stuff we talked about today, maybe more on the rotating equipment. So if you're able to attend, please do attend this. The sign-on details for that will be on the IMechE website, IMechE near you, and look at either Northwest or Northeast region. You'll find this event in there. Another event, 23rd of September, introduction to valves in the water industry. And final one, we look forward to hearing from you. So back to questions and answers. Anything on any hands?
I've not seen anything come in other than people saying thank you. And again, I think some of you have got our email addresses, and you can always follow up with questions, or if you want to start a conversation, I have no problem at all with that. We're just trying to help everybody.
I'm just putting my email address into chat if anyone wants follow up, but come back to any of the speakers. And what we want to try and do is see how we can make this industry more profitable and safer as well. I should have said that the different way around. Safer first, then more profitable. Let's make this industry safer, and the two going hand in hand.
Someone's asked if they can get a certificate. They'll be sent out automatically. I can't even be bothered to type it in. You'll get them. If you register attendee, you'll get a certificate. You'll get a copy of the slides, and you get a link to the YouTube video when it's done. I think, Alan, that's probably about it. And I think we have overrun by 22 minutes. So unless anybody's got anything else, I mean, I know I've been in the background, but thanks to all the other speakers. Brilliant topics. We could have done with an extra hour, I think, and we could have and a lot more chat. They were so good.
And we may do another something else where we can get together for a lot longer than this, and maybe even make it face to face, so it's much more interactive. So
yeah, it almost turned into a seminar, didn't it? But there you
go. But this is such a hot topic. It's contentious, and it's contentious for the right reasons. It's a hot topic, but we've all got the same intentions. We want our plants to stay safe, but we want them to stay operating as well.
And it's not UK only. It's not UK only. And tariffs and other things are hitting everybody. This is we need to survive, but we need to do it safely.
Yeah.
Okay. Any of the other speakers got anything they want to add before we draw it to a close?
No.
Yeah, it's Harry. Just to say that integrity is critical from a strategic point of view, but the reason that we've got failing companies in the UK isn't primarily integrity alone. So it's worth considering some of the other opportunities beyond integrity. And what can we do?
And Harry, I totally agree. And maybe we just need to think about, how we do that. And the whole point of this is, how do we do that as an IMechE? That's how this started. Is how do we do that as an IMechE?
And I mean, you kicked it off, Alan. But the biggest issue has been going on for years is the fragmentation of the industry from several very large operators who had large departments and experts. They suddenly all retired. A lot of the oil and gas industry just retired very, very quickly, and that expertise is not available. And people are trying to reinvent the wheel. They're not being able to share incidents and events between now what are separate companies and used to be under one roof. So So people are losing out on that training and that competence. And the IMechE, well, we're not a training organisation, but a lot of us have been around for a while. So we should try and figure out a better way to share that information and help people to stay competent and develop. And that's my take on this.
I totally agree, Richard. But I think a lot of the skills sit in the IMechE. So I'll just share this one slide, which I've used before. It's not my slide. Again, it's from the Tees Valley Combined Authority, but it just shows the level of fragment. This is Teesside. And, this just shows the level of fragmentation. 66 different companies in there and so on. If you looked at this 35 years ago, it would be very, very different. A much higher level of concentration, much more integrated chemical plants and so on, and not so many small operators. And that's before the hydrogen revolution starts and we get lots of small hydrogen producers pop up around the country and so on. So, and that's where I think the IMechE and MUA Energy Institute and so on need to play a part to make sure we retain knowledge, skills, and people are able to bring best practices across on those sites, because they're not the BPs or the Shells or the Chevrons on that list.
Yeah, and all the people in this webinar, although we've got day jobs, we're all volunteering on this stuff because we're worried about this and we want to help. Right, I think at that point we're just about half an hour overrun.
Okay.
Alan, so
okay, all right.
Thanks for chairing it.